All right, we'll go ahead and get started. So, just to give you a little bit of perspective about where we are in the course and what the material we're going to talk about today, how it fits into that. From a kind of a large perspective, we view the transport of small molecules and polymers depending on two factors. One is how many molecules you can dissolve in the polymer, and that's a thermodynamic contribution. And the other is, of the molecules that dissolve, how fast do they move through the polymer? And that's a diffusion or a kinetic phenomena. And so we've been talking about, we've been talking about the thermodynamic phenomena and how we describe and model thermodynamics of penetrants dissolving into polymers. And in the last couple of lectures, we've been talking about the diffusion phenomena. Once we're done with that, then we'll put this back together and start to talk about separations, controlled drug delivery, application areas that take advantage of these phenomena. And so today, we're going to talk a bit more about diffusion coefficients, and we're going to have a look at a little deeper look at how diffusion occurs and the impact of thermodynamics on diffusion coefficients. And this comes in through a so-called mobility factor that you'll see in the literature from time to time. And it starts with with the idea that there is another way of describing transport phenomena that we really don't talk about very much, called irreversible thermodynamics. Has anyone ever heard of that? No? Okay. Well, it's just as well. It's gone a little out of favor. It was all the rage in the 60s and 70s, and it's less and less used, in part because while it provides general and thermodynamically correct relationships between, for example, transport coefficients, it's very hard to use in a practical sense because it turns out to often have a large number of parameters that you're trying to fit to experimental data. But from that picture emerges a simple concept, and that is that diffusion of a molecule through a polymer, a sphere through a liquid, occurs as a result of two competing factors. One is there has to be some sort of driving force for the penetrant or particle to move in a certain direction. Usually this is a concentration gradient, or typically a chemical potential gradient, as shown down here at the bottom of the slide. And if a penetrant is subject to a chemical potential gradient that would have it move in a certain direction from high to low chemical potential or from high to low concentration, there is a rate at which it will move on average, and that's given by the velocity u sub x. And that motion is resisted by a force labeled F here. And in a macroscopic sense, if you imagine, for example, a half micron particle diffusing through water, that resistance is supplied by the water molecules that impede the progress of the particle. And you could model this force as being with Stokes' law, for example, for particles, and express it in terms of the radius of the particle. The same sort of picture is used at the molecular level as well to describe small molecule transport through polymers. And so the idea is that the driving force for mass transport, the chemical potential gradient, causes a velocity, a net velocity of a particle, and that the medium in which the particle or molecule is being transported through provides a resistance to its motion. And that can come, in the case of large particles, from just the macroscopic drag force around the particle. From molecules diffusing through a polymer, that resistance will come from the polymer segments typically executing thermally stimulated motions that open or that allow or don't allow motion to occur. We can write in a steady state situation that the flux of a penetrant through a polymer can be written just as is shown here. It's the velocity of the particle times its concentration, and if we put this on a weight basis, then the density of the mixture times the weight fraction of the penetrant is going to give you the concentration of the penetrant in, for example, grams per cc, and then if you know the velocity on average, then that gives the flux. And so we can essentially take this relationship at the bottom of the page and multiply both sides by the density and the weight fraction of the penetrant. We'll stay on a weight basis for now because it ties into an article that I'm going to share with you and we're going to go through in a moment. But you could also express this on a molar basis as shown in the middle of the slide by taking the weight basis flux and performing the unit conversions that convert it to a molar basis. But we'll look at the expression at the top of the slide and compare it to the standard expression for Fick's law of diffusion of a penetrant through a polymer based on a concentration gradient. And remember how Fick's law was established. Fick postulated that the mass flux would be proportional to the concentration gradient in analogy with Fourier's law of heat conduction and with Ohm's law of conduction electricity based upon salt diffusion through aqueous solutions, data that was reported by Sir Thomas Graham at some time earlier. And so this is an empirical model of how mass transport occurs. And we can, it's very effective. If the mixture density is approximately constant, you can bring that inside this derivative, and then this just becomes the concentration gradient, concentration of the penetrant. Now we can compare these two formulations on the next slide, the one on the right from Fick's law, and this one from irreversible thermodynamics that says that the flux is related to the gradient in chemical potential. And if we do that, then we can write the diffusion coefficient out of Fick's law, that is D, in terms of this frictional resistance to mass transport. And there's another term that shows up, and it's the derivative of the chemical potential with respect to the log of the concentration. This shows up naturally when you make this comparison of the fundamental relationship that mass transport is driven by a gradient in chemical potential with the Fick's law empirical description that flux depends on a concentration gradient. And what it tells us is that if you apply Fick's law to model, for example, diffusion coefficients in a given system, that diffusion coefficient doesn't depend simply on the kinetic resistance to transport of a penetrant through the polymer, but it also has a thermodynamic component to it. And this comes about from a very simple fact that if the mass flux depends on the gradient in chemical potential as shown up here on the left, but we use a model that writes the mass flux in terms of a concentration gradient, then the coefficient that is out front of the flux, that is the diffusion coefficient, has to absorb the difference. And so the diffusion coefficients that are often reported in the literature are based on Fick's law, and they have a contribution from thermodynamics, because the transport we recognize is driven more fundamentally by chemical potential gradients, but we often write the transport mass flux as being driven by concentration gradients. Now, in a lot of cases, this difference doesn't matter. The concentration gradient and the chemical potential gradient are aligned with one another, and they often change regularly. with one another. And so in a lot of cases, this factor will be small, or it will be a constant value, and you never see it in the experimental data, or it's not sorted out. It has been traditional to define the diffusion coefficient in this way, and rather than writing this frictional force like this, to define it in terms of mobility, which is RT over F. And so this is just a definition of penetrant mobility in the polymer, and it leaves the diffusion coefficient being defined as shown at the bottom of this slide. And so the higher is the mobility, the higher is the diffusion coefficient, and the lower is the frictional resistance of penetrant transport through the polymer. The reason for putting RT in here is because typically we would write the chemical potential in terms of the logarithm of the activity, and there would be a factor of RT that would appear up here when we write chemical potential in terms of activity, and it would cancel. And so the thermodynamic factor, alpha, is defined often in the literature as just the piece of the diffusion coefficient that is related to thermodynamics. And so you can write that the diffusion coefficient depends upon a mobility factor and a thermodynamic factor. Now, often, again, this thermodynamic factor changes little with penetrant concentration, for example. And so we typically discuss diffusion coefficients as changing mainly because of changes in the mobility in their environment. And I'll show you one example, though, where that is not the case, and where this formalism helps us understand the experimental data. Just before we get to that, we've expressed everything so far in terms of the weight fraction of the penetrant. You can also put this on a volume fraction basis, and I believe some of the papers in the literature do that. And this is just showing how to calculate these thermodynamic factors based on volume fraction. That's not going to be important for the discussion today, but just if you're reading the literature in this area, you'll see it both on a volume fraction and a weight fraction basis. And so the paper I'd like to talk about in this context is one by some colleagues at the University of Bologna. And they're studying the transport phenomena of two penetrants in this case. One is an alkane hydrocarbon, pentane, and the other is ethanol in poly-1-trimethylsilyl propyne, or PTMSP. And we've seen PTMSP before. It is often regarded as among the most permeable polymers that are known. It has a very low density. It's hydrocarbon-based polymer with silicon in the side chain. Has very low density on the order of 0.75 cc's per gram, typically very high uptakes of small molecules, and very fast rates of transport. And the interesting thing here is the behavior of the diffusion coefficient, or differences in behavior of the diffusion coefficients of these two penetrants in this very open and high free volume material. And I've underlined a few sentences from the abstract here. The first one, and you'll see a little Italian English here. In the case of ethanol, a non-monotonous behavior was observed. Well, I think it's probably exciting behavior as well. I think what he means, though, is non-monotonic. Right? Not that it's monotonous. Pentane's monotonous and ethanol is exciting, but that there's a non-monotonic trend with concentration, and also that the sorption isotherms are unusual, and we'll see that here in just a moment. This gives rise to different concentration dependencies for the solubility and also diffusion coefficients. And when you apply the mobility analysis and break out the diffusion coefficient into mobility and thermodynamic factor, you find that the unusual diffusion coefficient behaviors due to this thermodynamic effect and the mobility of pentane and ethanol change very monotonously with concentration. So here's the first piece of this puzzle. It's the solubility data. So this is just measuring how much uptake of these two penetrants, pentane and ethanol, you have at with a given pressure of gas in contact with these penetrants. Now, these particular studies have some practical relevance, although you won't see it in detail in this paper. So PTMSP has been was considered for some time as a membrane for removal of higher hydrocarbons from natural gas. It's way more permeable to highly soluble penetrants like butane and pentane than it is to light gas, poorly soluble molecules like methane. And so there have been some attempts to use it for that separation. It turns out that it is a glassy material with a very low density, that is a high free volume. It's not stable. Its properties change a lot with time. It undergoes what we call physical aging, where gradually the polymer simply consolidates and properties change with time. It's also been looked at for ethanol water separation. And so these are the two applications that were underpinning this particular choice of penetrants in this study. And because it's a glassy material, depending on the thermal history you give it, you can prepare it in different non-equilibrium states. And that's the difference between the filled and unfilled symbols here. The open symbols are in a so-called high density film that has been made by, I believe it's by thermal treatment, and the other data are for low density film. For the purpose of this analysis, it's not going to matter. But if you look at the shape of these isotherms, they're quite different from one another, and they're quite different from what I've been showing you for sorption isotherms in glassy polymers. Remember, we've talked about the dual mode model, and I've only shown you situations where the concentration goes up and bends over concave to the pressure axis. And indeed, that's what you typically see when small molecules sorb into glassy polymers. And it's what you observe with pentane, other hydrocarbons, other gases, light gases in PTMSP. It is not what's observed for ethanol. And so this is quite an unusual shape. If someone in my laboratory had brought those data to me the first time, I would send them back to remeasure them, because it wouldn't be obvious that this is kind of opposite the trend that you would initially expect. And what it shows is that as the pressure, gas pressure surrounding the film increases, that means the chemical potential outside the film is increasing. You don't need much of a pressure increase or a chemical potential increase to get pentane to sorb strongly to a significant extent in the polymer. You need a big change in chemical potential before ethanol will begin to partition significantly into this polymer. And then once you have some ethanol in the material, if you continue to raise the pressure and raise the chemical potential, then you see ethanol becomes much, it picks up a lot more ethanol with each increment in pressure, each increment in chemical potential. I had a roommate in college that was that way with beer. But anyway, that's a separate story. Now, our friends in Italy like to, being classical and very fundamentally oriented, they like to look at this kind of information on a chemical potential plot. I tend to like to see it as concentration versus pressure, but so they have put the data here in terms of the penetrant activity or chemical potential in the gas phase as a function of the uptake. And you can see for the pentane, which is shown in the data that still look a bit like the dual mode model, that you don't need much of a change in chemical potential before you get a significant amount of mass uptake. However, for the ethanol, which is the data at the top of the figure, you really need to raise the chemical potential quite a bit before you start to get any uptake. And then once it starts, once you get some ethanol in there, it's much easier to put the next increment of ethanol in. And so you can kind of see what's qualitatively, what the end story is going to be on this is that the very polar ethanol does not like to dissolve thermodynamically in this highly nonpolar hydrocarbon-like polymer. But as you start to put ethanol in that polymer, then the environment becomes more thermodynamically friendly for further molecules of ethanol to sorb. And these are the diffusion coefficient trends, and with concentration. And PTMSP shows behavior that is that's a bit unusual in the sense that the diffusion coefficients are decreasing as the concentration of penetrant goes up in the case of pentane. And this reflects the fact that this material has a very high non-equilibrium excess volume, and so as you put penetrants into the polymer, it doesn't swell much. And that means that its density is increasing, right? Because you're putting mass into the material but not changing the volume. And as the density increases, that means that the amount of free space in the material is going down, and that suppresses the transport of, for example, pentane. And so what our Italian colleagues had gotten excited about was the fact that while the pentane shows just a monotonic trend with concentration, that the ethanol diffusion coefficients did not. It had this, it has this dip in the middle, and they're like, well, you know, what's causing this? And what they found was that the thermodynamic factors, so you can calculate this from the sorption data, and the paper shows how to do that. I won't belabor it here. The thermodynamic behavior factor also has this dip in it because of the unusual shape of the sorption isotherm. And so then when you take the diffusion coefficients and divide them by the thermodynamic factor alpha, leaving only this kinetic mobility term left, the mobility scales very consistently with concentration. And it scales, has the same slope on this, this plot of log mobility versus mass fraction, the same slope for ethanol and pentane, and the only difference is whether the film is, has a lower or higher density. And so this is a case where this thermodynamic factor complicates the apparent behavior of the diffusion coefficient. The underlying frictional resistance to mass transport is going up as the concentration of either of these penetrants in the polymer goes up, and that just reflects a crowding phenomena that you're putting the penetrant in the polymer but not swelling it, and so there's less room for everybody to move around. And so the way they described this was that the strong energy interactions between the alcohol groups, unfavorable energy interactions oppose the dissolution process, and so you have to go to a high chemical potential increment in order to put any ethanol in the material. They suggest that this gives rise to clustering, and as you get more alcohol in the material, and that it becomes more favorable to dissolve alcohol in this polymer. As you go to higher concentrations. But the key point here was that this is a case where you can use this mobility and thermodynamic factor analysis to rationalize the diffusion coefficient data that would otherwise just present an unusual trend that would, that wouldn't be explained. We'll talk now, change topics a bit, but talk about free volume and quantification of free volume. It turns out that one of the most important parameters describing transport in a polymer is rates of transport, is the amount of free volume or open space that's available to assist penetrants to undergo molecular transport. We often estimate this in polymers based on the density of the material, which I'll show in just a moment. And I would say that after 30 years in this business, that if someone comes along with a new polymer and says, what do you guess its transport properties would be? The first piece of information I would want to know would be, what's the density? is with the density and the structure, you can make a rough estimate of what the free volume is, and then that kind of puts it into the constellation of where its transport properties will fall. And this concept goes back many years, as you'll see by some of these early publications. And the way you want to think about this is that polymer chains in an amorphous matrix are in a disordered state, and that there are gaps between the polymer chains and at polymer chain ends that form the free volume element. And there will be free volume elements or between polymer chains and between segments on a given polymer chain. Anton Petterlin talked about also the contributions of static and dynamic free volume. And so static free volume would be, okay, if you were to take a polymer and freeze it and not allow any molecular motion whatsoever, there would still be some regions in the material that were open space. And in principle, if you were a penetrant small enough, you could go through that topology without requiring any penetrant motion. That would be what Petterlin considered to be static free volume. Now the polymer chains are moving in ceaseless thermal motion, and this gives rise to a dynamic contribution to free volume that is often regarded as being responsible for penetrant transport or gating penetrant transport in polymers. It turns out we don't make much of a distinction between static and dynamic free volume, one because we can't measure them separately, at least in the laboratory, and two, because they're often highly correlated. If you have large levels of static free volume, then you're likely to have high levels of dynamic free volume as well, because the polymer chains are further apart and can in principle execute motion easier. A key paper in this area that outlines the underpinnings but also discusses the extraordinarily simple basis of this concept of free volume and what it does for diffusion is this paper by Cohen and Turnbull. And this is often referred to as the Cohen-Turnbull model of free volume. And what they were calculating based on statistical mechanics models was a relationship between a diffusion coefficient in a liquid of hard spheres and what they defined as the free volume. And so you can imagine if you had a liquid, if you will, a collection of hard spheres, they don't pack together with no volume, with no open space or free volume between them. Now you imagine these spheres endowed with thermal motion so that they're moving around and bumping into one another, and this gives an additional contribution to free volume. And Cohen and Turnbull derived this expression where the parameters A and what's in the numerator of the exponential turn out to be adjustable parameters for all intents and purposes in the actual use of this theory. And it is that the diffusion coefficient is related exponentially to the size of the minimum required volume for these spheres to execute a diffusion step. This we're going to associate with penetrant size, okay? And so it says that the bigger the penetrant size, the lower is the diffusion coefficient. That qualitatively is what we observe in practice. And VF is the free volume that is present in this liquid of hard spheres. So I'll show you data here in a moment about how this model is used to correlate diffusion coefficients and indeed permeation data in a wide variety of polymers. But I wanted you to see its simple beginnings. It comes from a very simple system of trying to track the diffusion of one hard sphere in a sea of other hard spheres undergoing thermally stimulated molecular motion. And you can look at the paper for the derivation. I'll just provide a couple of details here, and then we'll move into we'll move into the results. But the picture that emerges from this is, in the Cohen and Turnbull model, is given by the equation here in the center of this slide, that the diffusion coefficient depends upon P of V, which is the probability of finding a free volume element of size V, and F of V is then some measure of how much free volume elements of this size contribute to the diffusion coefficient. We're not going to worry about the details of that just right now. And that if the spheres had a certain volume, V star, that if there were free volume available that were smaller than that, it couldn't contribute to molecular motion. And so you're only integrating over free volume elements that are large enough to permit molecular motion. And so that's what V star is. Now again, without belaboring the mathematics, Cohen and Turnbull derived the expression that's in the middle of the page for the probability of finding a free volume element in this mixture of hard spheres, a free volume element of size V. And it depends upon three factors. One is, you can imagine that if you have a sphere, there is a certain amount of free space around it. And if you have its neighbor next to you, it also has a certain amount of free space around it, and there'll be a portion of that space that if you're just counting them one by one, you'll double count it. And so this overlap parameter, it turns out for practical purposes is treated as an empirically adjustable parameter, but gamma is there to avoid in the model double counting the free volume. And VF with the brackets around it is the average free volume in the system. And so this is a key result for the Cohen and Turnbull model, because it tells you how the probability of finding a free volume element depends on the average value of free volume and also on the size of the free volume element. And it says that large free volume elements are rare and small free volume elements are numerous. That is, as V increases, the probability of finding free volume elements of that size goes down dramatically. And there are two different pictures that we use to rationalize diffusion coefficients in polymers. One is this free volume approach. The other, which we've talked about briefly, is the activated state approach to diffusion, where we view diffusion as occurring over energy barriers and the activation energy of diffusion being related to how difficult or easy it is to open gaps in a polymer through which penetrants move. And what we'll see shortly is that these two pictures are really two different ways of describing the same phenomena, and they are strongly linked to one another. And so what you would find is, as the penetrant size goes up, or the required free volume element size to allow diffusion to occur goes up, the probability of finding those free volume elements of that size goes down. This will correspond in the activated state theory to the activation energy of diffusion going up as the penetrant size goes up, and finding sites that can allow diffusion of larger and larger molecules is increasingly rare. This graph shows one of the key features of this model that is helpful to explain a lot of experimental data in the field. And so it shows the normalized probability of finding a free volume element of size V as a function of the free volume element size. So I've just plotted that equation as shown here. And these three curves are how that probability changes as you increase the average free volume in the system. And what you can see is that if you're a really small penetrant, you only need a very small amount of free volume in order to diffuse, that even if the free volume is low, there's a high probability that there are available sites for diffusion to occur. Whereas if you're very large and the free volume is low, you're out of luck. It's incredibly rare to find in a low free volume material a big opening for a large molecule to go through. As you increase the average free volume in the system, then if you're tiny, it really doesn't make much difference. You have some more sites available, but you had a lot to start with. It's like giving Bill Gates an extra $100, right? It's not going to change things. However, if you're below the poverty line and you get an increase in free volume, it makes an enormous difference. And so what we tend to find is that larger penetrants are more sensitive to small changes in free volume than small penetrants are. And that if you have a system where you're transporting both small and large penetrants and you start to change the free volume of the polymer, you tend to increase the diffusion of the large guys a lot more than the smaller ones. And this can have significant ramifications for separations, because as you start to change the relative rates at which penetrance goes through, you start to change the ability of those molecules to perform, of the polymer to perform separations. And so the 2 points that are made here are ones that I made on the previous slide, so I won't belabor those here. Now, typically, when we use this model, we're not calculating these overlap parameters gamma, and the terms here in the front become essentially an empirical parameter A, and so you'll see this version of the model in the literature. And again, it has two features to it. It says that diffusion coefficients decrease exponentially with increasing penetrant size. So V star is the minimum size free volume hole that a given penetrant can go through. And so we take that as an indicator of penetrant size. Diffusion coefficients decrease exponentially as penetrant size go up, and inversely with free volume. So the more free volume there is, the higher is the diffusion coefficient, and it gets particularly higher for larger molecules. And so again, this is now starting to put it on in terms that are a bit closer to something that we might find in an actual application, but again showing the diffusion coefficient as a function of size. And I picked methane and butane because I'm going to show you an example here in a moment where in a polymer-based system we take systematic steps to increase the free volume, and we're studying the transport of methane and butane. And what you're going to find is that at higher free volume, there's less of a difference in the diffusion coefficients of methane and butane, and that has real implications on the separation properties. Before we do that, I'll just look briefly at the way we calculate free volume. And so the most common way of doing this is using the so-called group contribution method. How many of you have heard of group contribution methods in polymers? So, yeah, okay. So what do you know about it?
So you just add up like each contribution to each chemical group within the and come up with thermodynamic properties.
Yeah. So you break the monomer or the backbone structure of the polymer down into different chemical functional groups, and then there are factors that allow you to add the contributions of those functional groups up to calculate various thermodynamic and dynamic properties. This book by Van Crevelen, Properties of Polymers, is literally the Bible for these kind of group contribution methods. He uses group contribution methods to calculate virtually any property under the sun you can imagine for polymers: mechanical properties, thermodynamic properties, kinetic properties like transport phenomena, and on and on and on. It's like I don't know, the current edition maybe is over upwards of 1,000 pages, and it goes just chapter by chapter by different electrical properties of polymers and so forth and so on. It's a real resource. If you don't know, if you're trying to understand the contribution of given structural elements to properties of polymers, this is a great place to start. And the free volume in a polymer is often written in terms of the fractional free volume, which is by definition the specific volume of the polymer minus what's called the occupied volume divided by the specific volume of the polymer. So this occupied volume is the volume that is not available to assist in molecular transport. And so the difference between the specific volume and the occupied volume is going to be the so-called free volume in a polymer. And then it's usually expressed on a relative basis by dividing by the specific volume of the material. Now, V0 was established many years ago in a study where there was an attempt to correlate transport properties via group contribution method based upon the so-called van der Waals volume that can be calculated by group contribution methods in Van Crevelen. And the factor that gave the best agreement with the experimental data that relates the occupied volume to the van der Waals volume was 1.3. There is no other basis for that, but this is what's typically used in the field. And so we often write diffusion coefficients. Again, you see how we're moving away from the Cohen and Turnbull model towards something that is less precise from a molecular basis, but is more in line with what's used in the field, with A and B treated as empirical parameters. And so the reason that we use free volume theory is it doesn't work all the time, but it often works. It often allows one to rationalize the trends in how diffusion and permeation properties change across a range of polymers. And so these are just showing light gases and their diffusion in a series of aromatic polysulfones that have systematically different chemical structure. And as you go from one structure to another, those polymers have systematically different free volume and then different transport properties. And so as you go to materials that have higher and higher free volume, lower and lower density, then the diffusion coefficients go up, and it also turns out permeability, transport rates go up with them. Yes, Christina?
Would you say that the calculations are more reliable for glassy versus rubber polymers, or are they
Yeah, so the question is whether the calculations, these type of free volume calculations, are more reliable for rubbers or for glasses. The initial, historically, it's widely used for rubbery polymers. In more recent times, particularly for separations applications, glassy polymers were of more interest, and so it was applied more widely there. And you'll see these first examples are with glassy polymers, but then I'll show you a good one for rubbery polymers, ethylene oxide-based rubbery polymers. That's of any interest. So the benefit of this approach is it provides a way to rationalize transport data from different families of polymers and to compare one material to another. And so in the literature, these are all glassy polymers, polycarbonates, polyimides, and polysulfones. They're commercially used, some of them are commercially used as gas separation materials, and so there was a lot of structure property studies. Make a different polysulfone, a different polyimide, measure the transport properties, and you can line them up on a plot like this of CO2 permeability, for example, versus 1 over fractional free volume. And so this captures the data from a bunch of different polymers and puts it on a common or almost universal curve. Now you can see that there are points that are not on that line. And what this is reflecting is that free volume is often an important parameter in describing transport phenomena. It may not be the only parameter. And I would often say that, jokingly of course, that what we can't describe by changes in average free volume must be an effect of differences in free volume distribution. There's virtually no trend in experimental data you can't describe with those two levers at your command. Now, on the left, permeability is plotted versus free volume. Now, you'll recall that the Cohen-Turnbull model was not about permeability at all, right? It was about diffusion. Remember, permeability is solubility times diffusion. Here's the correlation with diffusivity. And the idea here is that as you change the structure from one polymer to another, often the changes in packing and in free volume and in diffusion, the changes in diffusion are much stronger than changes in solubility. And so then as diffusion coefficients go with free volume, so go permeability. And so you'll see in the literature often correlations of permeability with free volume. It's not because Cohen and Turnbull derived their original equation based on permeability. It's only based on diffusion. It's just that as you go from one structure to another, often the diffusion coefficients change way more than solubility, and so you get away with plotting permeability versus 1 over free volume. This is another similar plot that was originally prepared by colleagues in Australia. This is oxygen permeability again versus free volume, and I haven't put the names of the polymers on here. The thing that's remarkable about this is that it correlates oxygen permeability over close to 9 orders of magnitude, okay? And so you start over here with really low permeability materials like polyvinyl alcohol that's used in the wall of ketchup bottles because it's such a high barrier to oxygen, really low free volume. And it goes all the way through the gas separation materials and up to very high free volume materials like PTMSP and for Christina, PDMS, right, rubbery material. And so again, the utility of this concept of free volume is not that it is rigorously defined at a molecular and fundamental level. There is some inkling of connection to fundamental studies based on the Cohen and Turnbull approach, but it's simply that it often gives us a good way to line the data up and rank the materials. And so if you know, for example, the chemical structure and the density of a polymer, you can calculate its free volume and be within an order of magnitude of permeability. And that often, it's not always good enough, but it often is a good place to start. I'll give you a more complete table in the notes that are on Canvas of the van der Waals volumes that go into this calculation of V0 that further go into the calculation of free volumes. But you can see the kind of chemical structures that are given here and their increments in van der Waals volume. We'll show one example on slide 43 here. So this is a calculation of fractional free volume for bisphenol A polysulfone. So the bisphenol group is on the left-hand side, sulfone group on the right-hand side. This is the repeat unit of that polymer. It has a TG of 186, so it's a glassy material at room temperature, is a workhorse in hydrogen and air separation membranes by air products. And so we're going to calculate the free volume of this polymer. You can go into the laboratory and measure the density, and that turns out to be 1.24 grams per cc. Based on the chemical structure, you can go to Van Crevelin's tables and look up the increments to the so-called van der Waals volume to estimate the occupied volumes. The key thing to know about using Van Crevelin's method is that whenever you have a choice of more than one group, more than one way of breaking up the polymer into different structural elements, you always want to take the biggest group possible, because that gives one number for the van der Waals volume for a big chunk of the material. So in other words, there will be in Van Crevelen group contributions for methyl and for these carbons that are connected to 4 other carbons. But there's also a group contribution for this entire isopropyridine linkage, which is the carbon with the 2 methyls on it. And so when you have a choice of using the group contributions for methyl, and carbon, or a group contribution for the entire group, always take the entire group. Take the largest structural element that the tables provide. And in that context then, polysulfone has 4 para-connected aromatic rings. There are different van der Waals increments for ortho, meta, and para-connected aromatic rings. It has 1 sulfone linkage, 2 ethers, and 1 isopropyridine linkage. And for each of the para-connected aromatic rings, the van der Waals volume out of Van Crevelen's tables, 43.3 cc's per mole, 20.3 cc's per mole for the sulfone. These are the ethers. They're tiny at 5.5 cc's per mole, and then the isopropyridine group. And so you can calculate from the group contribution methods the so-called van der Waals volume, and that would be, essentially the volume that's occupied by the atoms and the electrons that doesn't permit any, any diffusion or penetrant overlap. Yes. Yeah. So then you need an estimate of what the structure is of the cross-link material, and what would be the smallest, not repeat unit, but the smallest structural element, and then you calculate based on that. Now, in a number of cases, for things like silicone rubber, when penetrants don't swell the rubber too much, the cross-links have almost no impact on the transport properties. They have a big impact on the mechanical properties. And so then you don't even need to worry about the cross-links. In other cases, like hydrogels that might be used in biological applications where the swelling is limited by the cross-links, then you have to be careful about how you account for those cross-links in estimates of free volume and transport phenomena. And we'll talk about those cases as we get a bit further. The molecular weight of this repeat unit is 442 grams per mole. We typically do the free volume calculations always on a per unit mass basis. And so we convert the van der Waals volume to a per unit mass basis, apply the factor of 1.3 to the van der Waals volume to get the so-called occupied volume, which is the volume that's not available for penetrant transport, and it's about 0.69 cc's per gram. The density of the polymer is 1.24 grams per cc, so its specific volume is 1 over that, or about 0.81 cc's per gram. So the difference between the occupied volume, 0.69 cc's per gram, and the actual specific volume of the material, about 0.81 cc's per gram, this is the free volume available for transport according to this method. And so we can then estimate the fractional free volume as shown here, and it's about 14%. And if you took 1 over 0.143, you could line up polysulfone on graphs like this one and estimate what its permeation properties. In fact, it's probably up there, but you could use that estimate of free volume to estimate what its transport properties were. These are some representative values. We'll see them more as we go along. Very open, high free volume material like PTMSP might have a free volume about 30%. That's really high for polymers. A lot of the polymers that are used for transport, like gas separation, are in the 14, 15, 20% range. PET, which is used in making the soda bottles, can exist in either an amorphous or a crystalline state. The crystalline state has much better chain packing of the polymers, and so in the crystalline region, the free volume is tiny, and there's no transport of small molecules through those crystalline regions as a result. To compare to some other materials like microporous carbon, polymers are not the highest surfaced area or most open materials known. And so there's lots of materials like carbon now zeolites and metal organic frameworks that would have much higher free volume than traditional polymers. And that has made those materials of some interest for transport properties now. There are limitations to this. There are not these van der Waals volumes. You go out and make some exotic structure that's never been made or considered before, there won't be a van der Waals increment or contribution to it. And there are some groups like the imide groups that are used in a lot of polyimides, for which there's some discrepancy in these van der Waals volumes, and so these things can cause this correlation to go awry. So you don't. It's not the law in terms of a physical law of nature, but it's a tool to use to correlate and rationalize data, and don't use it beyond that. Christina, here's an example of fractional free volume in a series of rubbery polymers. And these are materials that are acrylate-based copolymers. Polyethylene glycol diacrylate has 2 acrylate units, one on either end. Polyethylene glycol methyl ether acrylate has 1 acrylate unit. This would form a linear polymer if you polymerized it through these acrylate units. This is the cross-linker. And if you make mixtures of these two, then you polymerize them, you get a cross-link network with these methyl ether acrylate dangling ends in that network. And these materials are going from just the cross-linker polymerized by itself up to just this monomer polymerized by itself. They all make flexible films, likely in part because no matter how pure the monomer it is, it probably has a little bit of cross-linker in it from just the way it's made. And but in any event, as you go across the composition range at a temperature like 35 degrees C, the glass transition temperature of these materials varies, and as a result, the fractional free volume of the materials also varies. So the more of this PEG methyl ether acrylate you have in there, that is, you move left to right on this scale, the higher is the free volume, and T here is 35 degrees C, so the lower is the glass transition temperature. And these TGs are all well below ambient conditions. And so the picture that's emerging is, we would calculate this fractional free volume based upon the density of the material. And you say, okay, that's a static property, right? However, the dynamic, as you increase the free volume in this system, the glass transition temperature is dropping. So the chain dynamics are getting faster as well. And so often the static and dynamic free volume will go together, and then that's why we don't separate them. And the more of these dangling chain ends you put in there, that is, as you move left to right on this scale, the more open is the polymer matrix, and the lower is the glass transition temperature. And you might even imagine that these two properties are connected, right? That if you're a polymer chain that's moving around quite a bit, you might, in a static sense, need more space. So that chain motion is carving out additional static free volume. But there is a correlation here between the free volume and the glass transition temperature in these rubbery materials. There's a correlation in that same series of materials, correlation between diffusion coefficients and free volume. That's exactly what you would expect based on the free volume model that we're looking at. And if we put this into the context of the solution diffusion model, with the diffusion coefficient entering directly in the permeability, then the permeability model is shown down here. And it turns out that changes in free volume as you go across this family of materials is much greater than changes in solubility. And as a result of that, permeability really strongly tracks the diffusion coefficients. And we actually cheated a little bit on that in the sense that if you look at the structure of these two these two components that are going into this mixture, and you were to calculate on a weight basis, what is the weight fraction of ethylene oxide units in this monomer and in this cross-linker? They're both about 85 weight%. And so as you make mixtures of these two, then across the entire composition range, you're not really changing the chemical composition of the polymer so much. Now, if you picked different length cross-linker or different length monomer, that would not be the case. And that was why actually these were picked this way, was to be able to change the network topology without changing the chemical composition. Was it one variable at a time? And so we'll now look just briefly at the effect of penetrant concentration on free volume. And so here the issue is in many cases of practical interest, like the one I'm going to show you here is based on gas separation, but also in things like controlled drug delivery and hydrogels for medical applications and for water treatment, water purification membranes. The polymers absorb a lot of penetrant. It's not just a trace amount that, that doesn't do much to the polymer swelling or doesn't do much to the molecular dynamics in the polymer chains. There are also circumstances that are of great practical importance where the polymer absorbs a lot of penetrant, and then you can't ignore the impact of that concentration of penetrant in the polymer on the transport properties. And the simplest way to think about this in terms of free volume theory is you imagine if if you just have a polymer and there's no penetrant in it whatsoever, that the polymer chain segments would have their own free volume that would give rise to the fractional free volume you'd calculate, for example, using the group contribution method. If you start to put penetrants into that polymer, the penetrants bring their own free volume. And in rubbery polymers at least, you'll remember that you dilate the polymer matrix with every penetrant molecule you put into it, you swell it. And this is then going to change the free volume in the polymer. Often the penetrants will bring more free volume per unit mass than the polymer has. It's not always the case, but it's often the case. And that's simply because the penetrant molecules have a lot more molecular motion than the polymer segments that are constrained on either end by neighboring covalent bonds. And so the penetrants will often need more space or bring more free space with them as they dissolve into the polymer. And if you increase the swelling by putting penetrants into a polymer, like the rubbery polymers we're going to look at, this can also give the polymer chains more freedom to move. And you see that experimentally in a decreased glass transition temperature. The lower is the glass transition temperature, the more flexible the polymer segments are. Now, this relies on the fact that it's true when polymer chain motion is limited by free volume, that is by the intermolecular barriers to motion. In other words, I can't move because you're in my way, sort of thing. If I can't move simply because I'm old and stiff, then you won't see this last correlation. So, if they're intermolecular, strong intermolecular contributions to the glass transition, moving the polymer chains further apart won't necessarily increase the rates at which they move. But we're going to look at a case where, with flexible materials, as you increase the free volume, the polymer chain motion increases, the glass transition temperature goes down. We'll look at it in this particular, in the context of this particular paper and some related ones. And so, without going into a lot of detail, it is possible, there are models in the literature for estimating how the glass transition temperature of a polymer changes as you change the concentration of a penetrant dissolved in it. Now, there is a Flory-Fox model which says that 1 over the glass transition temperature of the polymer penetrant mixture is the weight fraction of polymer divided by the Tg of the polymer plus the weight fraction of penetrant divided by the Tg of the penetrant. That's a simple empirical model. There are more sophisticated statistical mechanics treatments, and this is one of those. This is a so-called Chow model. In the literature, you'll find it in this reference. And I don't want to belabor the basis of it, but just show you how to use it in these kind of calculations. And so Tg in this equation, equation 28 from Chow's work, is the glass transition temperature of a polymer penetrant mixture. And the idea here is as you mix penetrant with a polymer, it changes the glass transition temperature of the polymer. A good example of that is, how many of you have plastic water pipes in your apartment? Or yeah, this is white plastic. What are those made of? Yeah, polyvinyl chloride. It's a glass at room temperature. How many of you have an automobile with really nice soft vinyl in it? Okay, what is that? Soft vinyl in the car is the same material that's in the water pipes, polyvinyl chloride. The difference is that in the automobile, there's been a penetrant added to it. Something like dioctyl phthalate. It's called a plasticizer. And it's in there at fairly significant concentrations. We'll talk about that another day. And adding this dioctyl phthalate or related compounds to PVC softens the PVC. That is, reduces its modulus and reduces its glass transition temperature. And so the PVC water pipe that doesn't have plasticizer in it is a hard, rigid material. The PVC that has the plasticizer in it in your car is a soft, flexible material because its Tg is below room temperature. And then the last part of that story, what is the new car smell? In a new car, it always smells. It's the plasticizer coming out of the vinyl. So, and so you can see between those two examples that you may run into today, if you run into a nice piece of high quality, flexible vinyl in your car or some other piece of furniture, and you see a plastic water pipe, the same material. One has plasticizer, one does not. And so the idea here is that adding a low molar mass diluent, or we would call it a penetrant, can change the glass transition temperature of the polymer. And so the Chow model relates the glass transition temperature of the polymer penetrant mixture, Tg, to the glass transition temperature of the pure polymer by the equation that's shown on the right. And without going into a lot of detail, the thing that's important for us is that these parameters theta depend on the weight fraction of the penetrant in the polymer. The weight fraction can then, if you're reporting penetrant concentration in cc's at STP per cc of polymer, you can relate those concentrations to weight fraction. And essentially this gives a model for Tg versus weight fraction of penetrant in the polymer. All of the parameters can be determined experimentally, except for this parameter z, and Chow recommends a value of 2 for that. It turns out it doesn't much matter in terms of the Tg prediction, what value you use for z. But if we now look at the expression for the free volume expression for diffusion coefficients, and we can measure the density in that series of copolymers I showed you just a minute ago. And from the measured density at a given temperature, like room temperature, we can calculate a free volume at that temperature. We can also calculate or measure the glass transition temperature of each of those materials. And that allows us to develop a correlation between free volume and this T minus Tg. And what it suggests is that as the temperature goes down, the density of the material goes up, free volume goes down, material shrinks. And the reason this is going to be important is in just a moment I'll show you data taken at a range of temperatures, a range of concentrations, and you'll see that they all line up based on this picture. And then the glass transition temperature depends on the penetrant concentration using the Chow model. And so these are diffusion coefficients in a series of these materials now changing temperature, going from 35 degrees C down to, down to minus 20 degrees C. So over a range of temperatures, that model that we saw a moment ago allows us to see how the free volume shifts based upon just the shrinkage of the material as you go to low temperature. You see the diffusion coefficients line up exactly as you would expect based on free volume theory. Now we can use the Chow model to estimate how much the TG changes as we add more and more CO2 to these materials, because the CO2 will plasticize these polymers. And so now we go from a series of different polymers at a variety of temperatures to that same series of polymers at a variety of different temperatures, but also now with different levels of penetrant in them. And so now this picture of the way diffusion coefficients depend on free volume, you can line up the data on a dozen different polymers at five different temperatures and over a range of pressures as wide as you can measure. And you can put all the data on one correlation. It also turns out for CO2 in mixtures with hydrogen that you can measure both the diffusion coefficient in the presence and the absence of hydrogen, and all the data line up on that same trend line. This is the power of this approach, is it gives you, you can't predict what that slope is going to be or what its intercept is going to be. That's the A and B values. But once you have some data, you can use it then to predict the influence of temperature, composition, and concentration on diffusion coefficients and then transport. The same sort of approach can be used to estimate the impact of temperature and also CO2 content on hydrogen and methane permeability. It would be darn near impossible to measure hydrogen solubility in these polymers. The hydrogen solubility is too low. And so we can't correlate diffusion coefficients with free volume, but it works almost as well just to correlate permeability directly. And this is using the free volume values that are calculated using the models I just shown you. If you look at a range of different penetrants, this parameter that is in the free volume model, remember there was a V star up here that the diffusion coefficients decreased as penetrant size went up, or this B parameter goes up with penetrant size. Well, here's a correlation of B with the cross-sectional area of the penetrant over the Lennard-Jones penetrant diameter squared over a range of penetrants. And the permeability also correlates well with free volume, again, because the solubility changes very little among these the series of materials. We're going to talk about next time, it's right at 9:15, but I want to talk next time about relating this picture based on free volume and tying it back to the activated state theory of diffusion, which is the other approach used to describe diffusion coefficients. But we'll stop on this little cliffhanger here.